Hello everyone, this is Ankush here. Welcome to the first one in the series. Welcome to the educational webinar of MIDAS GTS. So here we begin. For those who are the new users who haven't used MIDAS GTS before, I bet this is going to be a new experience for them. So I'm Ankush Sharma and I'm a civil engineer by profession. So about GTS, if I'm asked 4 words to describe GTS, I will say convenient, rapid, accurate and productive. It is convenient and rapid in modeling, accurate analysis and productivity. What else you can get, what else you want with so advanced post-processing results display. So in short, GTS is a total state-of-art solution which has been developed through integrating all functions which are required for structural analysis of geotechnical and tunnel engineering. Its capabilities include stress analysis, reflecting, construction stage analysis, seepage analysis, and much more, which I will be demonstrating today, and you will yourself come to know what MIDAS GTS is all about. So I will begin with a small introduction about the GUI, the geometric modeling, the meshing, moving over to the property and the element type, the analysis types, and lastly ending with a small note on the wizards which MIDAS GTS provides. So beginning with the introduction of the framework. In MIDAS GTS we have the works tree window where everything is listed in an hierarchical order. We have the property window where every property of every element you enter in the work window, it will be highlighted in the property window. So this is our main work window. You have task pane window which lets you know how to in a defined sequence how to go ahead with the modeling and meshing. We have the table window and we have the output window. Other things we have main menu, standard toolbar, the selection toolbar which we usually use to select various elements in our model, the work plane toolbars, how to move the work plane, how to change the settings, the snap toolbar to select it is also a very useful selection tool, the tab toolbars and the view toolbars with which you can have various view of the model, the various perspective views, and the measure toolbar with the help of which you can measure the distances between the points in either a single plane or even a 3D plane. Not only this, you can have the angle measurement too. So I will be demonstrating this measure toolbar in my demonstration. You can change the unit system directly through the unit system toolbars. So in the display mode, we can a single mesh which is shading by default. We can display the mesh in a wireframe mode, in a shading mode, in a future edge with shading, and 3-phase wireframe works. So this is how it will look in a single meshing, which is initially in shaded format, how it will look in different formats. The view toolbar. We have the dynamic view which allows you to move, rotate and zoom the work window. We have the dynamic zoom. We have the dynamic pan which is just used to move the viewpoint. These all view toolbars are very essential for just a basic learning of the modeling. But after that you start using some of the shortcuts. You start selecting control, you start using control and the right key to which will replace these view toolbars. But in the starting, using these toolbars is really important. So we have dynamic rotation with the help of which you can rotate the viewpoints. Select and the unselect tools, because when you are dealing with thousands and lakhs and millions of elements, you need to have very specific selection toolbars. So we have the select toolbar, unselect toolbar with which you can select anything, unselect all, different selecting tools to assess the user with the selection procedures, like you can include the intersected ones in a circle, polyline displayed, and the most importantly the selection filter, with the help of which you can select according to their nature, whether it is a shape, solid, shell. And this thing is very important when a single solid say has many other elements in it. by which I mean to say a solid is composed of a shell is composed of a face is composed of several wire is composed of edges is composed of point. So when you want to have a specific selection, you want to select a solid, so you can just make the selection filter, and this will make the selection of your very easy. Just hold on a second, we have some of the queries. Okay, so I will handle all the queries at the end of this presentation. So till then, you hold on with your questions and everything you have in mind. So we have the snap toolbar, which give convenience by using geometry, grid or element tools. We have the grid, vertex, which you can select by end, middle and several others. So let's move with geometry modeling. What's the basic of geometry modeling? Let's define how we use GTS. We plan the project, then we model the project in either 2D or 3D, and after we have done the modeling, we go and mesh it. So I will be describing, this is the main the extent of what I will be doing in my today's presentation, taking care of all the geometry modeling, the mesh modeling. So discussing the types of geometry shape, we have point, which is a basic type. We have curve, surface, solid, which is a 3D element defined with volume, and compound, in which different elements are listed in groups. So in the order of the generation, we have this hierarchy, but in explosion, we have the opposite hierarchy. So exploding a solid will give me faces or shell. This is the sub level of a solid. So moving with point, a point is a basic element of all shapes. As we know, each curve has point, each curve is made by joining 2 points, surface is made by joining 4 points, solid 4 points. But the use of points becomes very important when we need to account for the imprinted points, which is very important in case of when we are working with piles in some excavation projects. So without these imprinting of piles, there will be no connectivity between the nodes. So with imprinting, the generated nodes will have connectivity between them. Moving to the curve. Curve is a curve or edge, line or curve connecting 2 points, which is as basic as point, and wire is a group of continuous edges. So from each curve we can create face, and from wire we can create solids. So there are several ways of creating a surface, which is the next in our hierarchy. After point and curve, we can create a surface by using plane patch, which takes into account the coplanar curves. We can create a surface by using grid patch, which uses very undented form of the ground. We can create a surface using the vertex cloud. By vertex cloud, it's a dispersed mode of points and just 3D space. So using all these 3D input of points, we can create a surface. We can create a surface using nose patch, and the more advanced using Coons patch. Moving over to the solid, GTS provides the most primitive types: the cylinder, cone, box, wedge, sphere and torus. Apart from these primitive types, you can also generate a solid from any primitive. You can create trim a primitive solid or a divide a primitive solid, and even you can work around with the Boolean operations using the fuse, cut, common, and dividing at multiple surfaces. By this thing you can create the desired shape as you want for your project. These all solid generation model features I will be demonstrating in my coming demonstration. So as I said, a solid has several subpoints, which is 8 in number in this case. It has several subedges, it has several subwires, it has several subfaces and subshells. That's why here comes the usage of the selection filter, as I already highlighted. So moving further, co-shape. Two faces need to share a edge, which is called a co-edge. and two solids need to share a face which is called a co-face. So this checking duplicates becomes very important in modeling, because this is the first step with which we ensure that our two solids are connected to each other. That is, when we go for meshing, there will be connectivity between the nodes and two solids. It is very important checkpoint that after solids we go for always duplicate check, so that we can see the duplicate faces to account for the sharing of face between two solids. And if there is a duplicate, then which means there is connectivity, and which means we are not going to have any problem with the nodal connectivities in our meshing. So moving over to some of the advanced features we can do with the basic shapes. We can merge two edges to create a single edge. Now the single edge will have no subpoint but only the edge subpoints, no middle subpoint. We can extend a curve and perpendicular to a base entity, and this is the extended edge. We can make a wire from several faces, and then from a wire we can just in one shot we can create a solid by using some of the extrusion functions. So, and we can sew two surfaces to create a single surface. So it will be a single surface. It won't have a separate identity of two surfaces. Now the two surfaces have been clubbed together by using sew surface, and MIDAS GTS provides this function. Now it has one shell and two subfaces. You can trim the solid with the help of which you specify the trim surface, specify the reference point, and the opposite solid will be trimmed. So this is very useful. This comes very useful when you need to generate model different geometry model for your projects. Moving further, we have another method of generation of solid called the divide function. With the divide function, we can divide the solid into two halves, and each solid will have a different entity. We specify the tool surface, and on the basis of the tool surface we divide the solid. Embed. If two solids share a common area, like we have a tool object and master object, and it was supposed to be embedded in the master object. Let's say the tool object is our tunnel, and the master object in this case is our ground. So that common area should not be overlapped. So we need to embed the tunnel in the so-called ground, which is our master object. So using embed function, we embed the tool object into the master object, and thus the overlapping areas are removed. The explode, as I said, each solid will be exploded to its sub-solids using the explode feature. So using explode, we can explode the solid into several faces and then use each face at our will. Extrude. From a 2D geometry, we can extrude a 3D solid. So from a single wire, we can use the extrude function and generate a solid of a desired shape. So this becomes very important when we just input the 2D DXF files from AutoCAD, and then using those 2D shapes, we can extrude the whole solid. We can generate the solid by revolving along some revolution axis. The solid can also be generated by using the loft function. These all features I will be demonstrating in the coming slides. So we just specify the starting and the ending profiles, and on the basis of that we generate the whole solid using the loft function. The C feature, in which we just specify the cross section which need to be swept along a guideline. So the solid, this is a very good mode of generating a solid again. Apart from that, GTS also provides several modifier features with the help of which you can trim two surfaces. Then you can do some of the modification. You can work with local prism, draft, provide chamfer, provide offset. And when the modeling is complete, even in the 2D case or the 3D modeling, you need to play around with the position of that, moving that geometry to the desired position. So we use several features like several transform features of GTS, mainly the translate, with which we specify the direction, and if we translate using uniform copy, it will be translated in the desired direction. We can rotate the geometry. So on a rotation of 90 degree, it has been rotated. It's very clear. Next, we can mirror. For symmetric geometries, we can just model one part of the whole geometry, and then we can use the mirror function. So a solid which is symmetric, we can using a mirror function, we can generate the whole solid. So in this case, the mirror plane was YZ plane. In GTS, you can the selection of planes becomes very handy when with the various options GTS provides you to select various selection tools, various view planes. Using all of them, this selection and this modeling becomes a very easy task. But you need to be expert at what you are doing. So in another way of transforming is scaling. You can scale a geometry to another shape, like in this case the initial rectangle has been scaled to twice its own dimension, specifying the scale center point which will remain fixed, and rest all geometry will be scaled. As I said previously, the most important after the whole modeling is complete, after you have generated all the desired shapes, so the most important part is check duplicates. You need to have co-faces between the solids. So if there are 3 solids in our case, there need to be have co-faces between them. If they don't have, which means they don't have connectivity. Like if they have co-faces, there exist some duplicates. There is no problem with the nodal connectivity in meshing. It's very good. So, but if you don't have any co-phase, then there exists some nodal connectivity, and because of this nodal connectivity, it's very hard to find where you have committed a mistake. So the best way is delete all the meshing and check the duplicates. And GTS also provides you with the terrain geometry maker, with the help of which you can generate the terrain from digital maps. You can import the digital map and terrain geometry maker, and from with the help of which you can actually create the surface which is there in that digital map, which has been provided by some ArcGIS or ArcMap softwares. The data exchanges, working with softwares becomes the data exchanges become very important, because this is not the only software you are using. You need to interact with others too. So GTS provides you with various import options like STEP, IGS, BREP, the DXF files, 2D and 3D, and the neutral format files. Apart from this, you can also import the IGS files. You can export the geometry to STEP, IGS, BREP, and the neutral format files. The full forms of all these I have shown on my screen. If you are previously some MIDAS program user like MIDAS Civil and MIDAS Gen, you can benefit yourself by using the MCS format. You can interact with various MIDAS softwares we have in the market. You can interact with the solid wizard. You can import files from the solid wizard from Civil and Gen, and then having that solid, you can go for higher meshing and GTS. So before I begin with meshing, let's go and have some demonstration. As I explained, this is the main menu. These are the different tab toolbars with the help of which I can do everything which I plan to do through the main menu. So let's start a new project. First, with the project settings, here you can define the project title, name, take care of the unit system you need in your modeling. take care of the 2D, 3D type, and this is the most important feature which actually the user ignores. Whenever you need to go for the eigenvalue analysis, you need to convert your weights into masses, and here is that option. So after doing everything, we click OK, and here we begin. So here we'll see all the geometry features, the various primitive features with MIDAS GTS provide: the cylinder, solid, cylinder, cone, box, wedge, sphere, torus. You can also access these solids through the tab toolbar, and there are various generator features. You can extrude, as I said, you can extrude the whole solid from a 2D geometry using extrude, revolve, loft, and sweep. So let's try this. Okay, sorry, there I think some mishap happened with our program. Let's open it again. No worries. So I will be briefly going over the various geometry features. So let's begin with the basic curve in our case. So I will be making a face using the make face function. I can have a face in my case using the snap toolbar. So we have a face in this case. So let's select translate. So you need to let's specify the direction. So as I will be modeling 4 solids from using the basic 2D geometry, so let's copy the solid in various directions. So this is what we have. So my purpose here is I want to generate the whole solid using extrude feature. Select the solid, select extrusion direction. You can also specify the direction using 2-point vector. And even if you want to go in the opposite direction, you can specify the reverse direction. And before, this is a very good practice that before you do everything, GTS provides you with the option of view option, that to view actually what you are going to model. So here we are done with the first solid. Then geometry, generator feature, revolve. Now we are going to revolve this geometry along a revolution axis. We specify this revolution axis. Now the defined location again becomes very important. Where we want this axis to be. Either we want the rotation along the axis passing through origin, or the axis passes through one of its edges. So let's axis passing through one of its edges. Let the angle be 180, and here we are done with our next solid. That's what I was emphasizing, how easy the modeling becomes using various generator features, where you can generate the whole solid using extrude, revolve, loft, or sweep. So the next on the list is we'll be using loft feature. So for loft feature, as I emphasized, we need to have two solid. We need to have the starting and the ending profiles. So let's translate it. You can go and transform, translate, and the shortcut is Control 1. You specify the direction, and you want to copy it. Copy a uniform copy. Oh, generator. So let's translate again. I think we didn't finalize it. So you make a uniform copy, view what you're doing, and apply. So we have a view. Let's scale it again. Geometry, transform, scale. Now we are going to scale this solid to double its size, and the scale center point will be this time, which is going to stay fixed. View and apply. So now we have the starting and the ending profiles, and now we can use the our loft feature, where we specify our starting profile, ending profile, have different ordering methods in which I will be going for the selection, view, and apply. So next in the list is the sweep feature, for which we need to have a curve along which we want to sweep our 2D geometry. So let's see the usage of this work plane. Now let's rotate this work plane. There are many ways to rotate this work plane to our desired profile. You can go work plane, go and move, then specify some of the angles, or you can simply go to model tab, go to work plane. Now I want the work plane in XY plane, and it's there. So the curve, let's draw is 2D spline curve. This 2D spline curve will be drawn on this work plane. So you specify the start point and draw it. So geometry, you are going to sweep. Here I will highlight the use of the selection filter. If I have edge, it's difficult to select every edge individually. Go to the selection filter, select the wire, select in the profile in one shot, select the curve, sweep mode, which is corrected, frenette or fixed, transition mode, right corner along the right corner, view what you're doing, and here we apply. So we have generated all the solids using from the 2D geometry using several generator features. Let's go and see how we can now play around with these shapes and create a shape of our desired profile using the trim, divide, and embed features. So for this thing, we'll again bring the work plane to XZ plane, because for this we need to create a surface along which we are going to trim or divide the surfaces. So make face, and one for, let's say, the spline one. So let's see, we'll translate this shape to the middle of the solid one. So the length of solid one is 200. I'm translating to moving it to the middle. You can so we are there. Next we are going to trim the solid along the trim surface. So solid, trim, we specify the solid, we specify the trim surface on the basis of the reference point. Like if my reference point is on front side of the trim surface view, it will be my plane. But if my reference point is on rear side of the reference surface plane, so we trim the solid to the required shape. Now we need to translate. Let's now have a look on using the divide feature, how you can divide the solid into several sub-solids. So for this we need to translate this dividing surface along this profile. So even GTS provides you with this feature, sweep translate, where you can translate the surface along a desired profile. So you select the shape, select the curve, specify the number of divisions, specify the base sweep point, view, and apply. So we have translated the dividing surfaces into number of parts we wanted. So now geometry, solid, divide. We are going to divide this solid using the two surfaces which are inside, which actually divide the solid. This feature, the divide touching faces of neighbors. This becomes important when you have when you are dividing a particular solid, but you are not dividing the neighboring solids. Like in a tunnel, for tunneling, you want to divide the solid as per different excavation stages. You want to excavate the tunnel in different excavation stages. So in that, you are dividing the tunnel and you specify the ground as neighboring faces of neighbors. With using this feature, you again ensure that there is nodal connectivity in meshing. So we view and apply. So this is what we have done. We have, from a single solid, we have divided the solid into several small solids along the dividing surfaces. So this was different ways of creating geometry using generator feature, primitive features, and then using the trim and the divide features. Let's see the modify features. After you have the geometry, how you can play around with different modification features. So for this, I'll be creating a primitive geometry. Let's say box and apply. And we are going to translate it because I will be showing various primitive geometries. We are going to translate it in y direction, say for 6 times. Here we have all of them. So geometry, the fillet feature. Now to sharp edges, you can even provide smooth curves. So specify the edges. This is what you have done. From a sharp edged solid, you have created a smooth edged solid, because nowhere in the practical geometry you have sharp edges. You need to put some of the smooth edges. Next modifier feature is chamfer, where you provide some of the chamfer to the solid, a slope. So this is what we can do using chamfer. Next in the list, we have offset draft. Let's select the object, select the face, reference frame. Either you can select it directly, but I want to emphasize the use of 3-point plane. Specify the 3 points on the plane and specify the draft angle for how much you want the incline. And you have drafted your solid with a particular angle. So next in the list is your shell, which is very basic. You select the whole solid, select, and you can create a shell out of that solid that will be bounding the whole solid. But I will show the use of local prism. So for local prism, we need a prism profile. So let's create a prism profile. Move your work plane to the top of the solid, and it's there. Go perpendicular to the work plane, create a surface, create a rectangle using make feature. So or you can do one thing apart from using this thing. Let's create a small circle on this thing, and I will extrude the whole circle. I will just cut the whole tunnel through the solid using prism function. So let's have a circular profile for your prism, and here we are done. Geometry, local prism. You are going to cut, you specify the base face, you specify the prism profile, you specify the prism direction, which is in my case going to be perpendicular, the z-axis, and different modes with the help of which you can actually have difference in extruding heights. Like if I have 2 or 3 profiles on my face, you can extrude, you can cut the solid in the required direction using several features up to a particular height or through all. So here I will be using it through all, and okay. So let's see what we have created. We have, using a prism, we have actually cut the whole circular cross-section tunnel from our solid. So next on the list is, we will see the usage of various Boolean operations. So for this, let's see, create a sphere of radius say 50 and the screen snap, with which you can actually move in the whole screen where you want to provide the sphere. So using Boolean operations, as it's very clear from fuse, we are going to fuse 2 different solids having 2 different entities into one solid. So if I select it, it's just no more 2 solid. It has one ID and has one type. Next in the list is using cut feature. And apply. You can cut one master solid with a tool solid with the surface of a tool solid. Next in the list is, you can just take care of the common surface you have and there. So it's there. So these are different ways of modifying the solid which you have already created using some of the primitive feature of the generator feature. And then in the list is, after you have done everything, the next important feature in geometry is shape. You can change the color of every shape you have. Select all the shapes and then you can assign different colors accordingly. Next I will be demonstrating my art terrain geometry maker. So run the terrain. How we can import a digital, how we can import the ground surface from a digital profile. I will be importing a digital image. Let's import a digital image. It's an AutoCAD DXF file. And here I will demonstrate how even from the real geometry you can use the geometry surface and you can actually simulate the whole simulate the actual ground surface in GTS. So this is the form of the digital image we get. It has several contour lines on it. So I will specify the surface with which I am concerned. Select base contours. Now we specify a plot zone. And this will be the surface of the ground which I will be importing into my GTS. Okay. So it's preparing the faces depending on different contours and depending on the required plot zone. So we are going to export it. So in GTS, let's hide all these solids and even the curves. So in GTS we can import this surface using import function. the whole surface is here, and from this thing if you want to create a solid, so all you have to do is you have to change your work plane, having work plane in XY plane, and then using the curve make a face, specifying the 2, and this face will be created on the work plane. So I will use this face to extrude a rectangular geometry, and then I will trim that geometry using the surface. So geometry, generator feature, extrude, select direction. You can use 2-point vector, and in 2-point vector just select the Z direction. And say that length is around 1000 because, and apply. So we have the solid with us and we have a trim surface. So the last thing we are left to do is divide the solid along this trim surface. As I said, reference point, go to view, and here's the whole solid in front of you with the actual geometry which is present on the ground. And now you can view this geometry by using several view features. You can display the wireframe only of this feature. You can even have shading, and you can even control the transparency of the shape, because when you are working with several solids you need to take care of the transparency. You can control the color of the solid, and this is how you can play around with the look of the solid which you have already created using several geometry features. So let's go back to the presentation and move to our meshing. So the meshing in GTS, we can do the meshing by using auto mesher, using map mesher, or you can protrude the 3D mesh from a 2D generated mesh which has been generated using auto mesh or the map mesh, and then finally you can again manipulate the generated meshes. So with auto mesher in 2D case, GTS provides in GTS you can create a 2D auto mesh using loop mesher, the Delaunay mesher, or the grid mesher, which are almost the same which I think for a new person they look almost the same, but when you deal with very advanced projects, their usage may differ, because they differ in their regularity, uniformity, they differ in their orientations and sensitivity, they differ in their sizing controls. So you can mesh different solids using a loop mesher, a grid mesher, or even taking care of center points using Delaunay mesher. And in all of these meshes you can either go for a triangular, which is actually 3-node 2D mesher, or you can even go for a higher order mesher creating 6-node 2D meshing. But along with the triangular low order and the high order, you can also go for the 4-nodal quadrilateral and even the high ordered 8-nodal quadrilateral meshing using auto mesher. Auto meshing for 3D, going into some of the stats, GTS tetra mesher auto generates tetra solid meshes with variable sizes and smooth transition. The rate is approximately 2 lakh tetras per minute. So using auto mesher in 3D, we generate 4-nodal tetrahedron, or even we can go for non-linear elements, or the so-called quadrilateral elements, which is also called high order meshing, creating 10-nodal tetrahedrons. Along with that, you can also take care of the smooth transition as well as take care of the holes and the curves which are present inside the solid. With map meshing, you can generate a structured mesh both in regular and orthogonal shape, and you can generate a structured mesh both in surfaces and solids. By structured mesh, we can generate 6 nodal hexahedron in linear format or 20 nodal hexahedrons in quadrilateral formats. And along with that, you can have the full control over the whole meshing. This is actually what you say mapping the whole mesh. Automeshing is it automatically do some things, as very clear from the names. So you can map mesh a solid using either case-sided edge. Map meshing becomes very important in case of tunnel lining, or you can use map mesher to protrude a 3D meshing from a 2D map meshed cross section to generate 8 nodal hexahedrons. So the size control becomes very important when you work with map mesher, and it also becomes important when you work with auto mesher, because sometimes you want to have very fine meshing in some of the areas, like and around the tunnel you want very fine meshing, but away from the tunnels this meshing can go coarse. So you specify the size control of the meshing, and different ways of specifying size control. You specify the uniform size, number of divisions, the linear grading, where you specify the start length of the element, the ending length, and the number of divisions. And also you can have a symmetric seeding. And then you can also play around with the refinement factor, where you can refine your mesh to either very fine meshing or very coarse meshing. So different ways in which you can assign size controllers along edge. Just select the edge, specify the number of divisions you want on that edge, and you do the size control. Or you can also custom your size along the selected edges. You specify the distances you require. Then from an edge on which you have already done the size control, you can match edge seeds using match edge seed function. You just specify the target edge and the source edge. So after you have done the size control, now you need to do the map meshing. So using map mesh key edge area, you can map mesh the whole solid using 4 nodal quadrilaterals in low order meshing or 8 nodal quadrilaterals in high order meshing. The protrude mesh feature of GTS from a 2D mesh, which is either map meshed or auto meshed. You can protrude a 3D mesh, creating 8 nodal hexahedrons in low order meshing and 20 nodal hexahedrons in high order meshing. So you extrude it. Even you can use protrude mesh feature. Just specify the edges, specify the size controls, and fill the meshes in between those edges. From a 2D mesh, you can use revolve feature and create a 3D mesh. So these protruding mesh feature becomes very important in cases where you are not going for modeling the whole geometry first and then you doing the meshing. In these cases, you just do the meshing for 2D cross section, and then you may protrude that meshes to create a 3D meshed 3D mesh solid. Thus in those cases we avoid going into the 3D core modeling. Or we can also protrude a 2D mesh along a guideline to create a 3D mesh. Others in the list are: you can project a 2D mesh on a surface to create a 3D mesh. From a 2D mesh, you can use the offset and the thickness or the offset you need to create a offset mesh in 3D. After you have done all those things, after you have meshed, meshed either going by the auto mesher or the map mesher, or either using several protrusion features, you can play around with merge mesh set, where different meshes can be merged as easily. Suppose we have 3 meshes and we want to merge it into 2 mesh sets. So just select those mesh sets and drag and drop. They all will be merged in one mesh set. Another feature is merge node, because as I said, sometimes nodal connectivity is very important, but sometimes due to even you are taking your maximum care taking care of the geometry, checking the duplicates. You might leave some of the nodes that are not connected to each other, in which there is no nodal connectivity. So you can merge those nodes to have a more structured mesh. So this merging is either done by the average distances between them, or you just specify the node which you want to retain and you move the another node. Next on the list is extracting element. Either you extract from a mesh or you extract the element from a 3D solid which has already been meshed. Then you select just the faces of that solid, and from that you extract a 2D element. This features becomes very important because with this thing you are already taking care of the nodal connectivity. You don't have to take into account, you don't have to worry about the nodal connectivity. And this thing is very important when it comes to provide the tunnel lining. You have to provide tunnel lining inside the inner surface of the tunnel. So from the mesh tunnel solids, you can directly extract the element to generate a 2D lining, or you can also extract the element selecting the nodes, because if you are using some of the protrusion feature, in that case you don't have a 3D geometry. All you have is a 2D mesh surface, and from where you create a 3D meshed solid, and from that 3D mesh you extract a 2D mesh from their nodes. Again, if they are symmetric solids, you just mesh a particular part and then use mirror feature to mesh the symmetric parts. You can and GTS also provides the scale feature with which the original mesh can be scaled to the required dimensions. So the basic fundament is, before I go to my meshing demonstration, I would just like to explain in brief. There are two ways of modeling I have discussed. First, you plan everything, create the section, which you can do by either using polyline, line, or either import DXF from AutoCAD. Then you create a solid from that section using either extrude, loft, or several generator features which MIDAS GTS has. Then from that solid, if you want to do some of the modifications with that solid, like some of the Boolean operations or the embed, divide, trim, and now you have the final geometry with you. You do the size control using size control along edge, size control using match edge seed or the custom edge, and after you do size, you generate mesh, which means you do the whole 3D modeling first and then you do the meshing. Or the next way of doing proceeding is the mesh modeling, where you create the section again using polyline or importing some of the DXF files. You generate a 2D mesh now using auto mesh planar area or KH area. With auto mesh, you, as I said, you can have 3 nodal or the 4 nodal low order meshing elements, and from that you can actually extrude in the required direction to create the pentrahedral 6 nodal pentrahedral elements, so which I will be demonstrating in my demonstration. So from a 2D mesh, you use several protrusion features to extract a 3D mesh, and then you transform this whole extracted 3D mesh to the required shape. You mirror, translate, or rotate it to the desired profile. After you have done every meshing, the most important thing is this, which will let you know that how accurate your meshing is, whether there is nodal connectivity between several surfaces, whether there is nodal connectivity between several solids in your whole model. So you need to do the check mesh. So for 2D meshing, we go for checking the free edges, which will be displayed in red, and if there are free edges, which means your meshing is not good, you need to remesh again. And for 3D meshing, we check the free faces, and which will be displayed in orange. So if there are free faces, there's no point of going ahead because the solver is going to crash. You should go back, check the discrepancy in your modeling using some of the duplicate features, or you start again. This is all you can do. So before I move to element type, let's go and do some of the meshing. Let's start a new project. Let's first explain what's the difference between a auto mesher and a map mesher. So let's create the simplest solid we have. We have two cubes. One I'm going to auto mesh using auto mesh solid, having an element size say 20. Let's the attribute, you need to define the properties, which I will be explaining in my coming slides. So you don't worry about this thing. For now, we give it a default value of 1 for 3D meshing, and for 2D meshing, we give it a default value of 2. And after you have done all the meshing, if you are not, you haven't input your attributes, you can go and change model element and change attributes where you can specify the new attributes you have. So for right now, I will be using a default attribute, or even you can go and create the whole attribute if you wish to. So we have a solid, go for the advanced features. In the solid, if I want to go for the high order meshing, we can generate mid side nodes, and this with after checking this option, I'm going to have my high order meshing. Just view and apply. So we have auto meshed our solid. Let's now map mesh the other one. Now let's see on a single element. I'm going to select a single element from an auto mesh solid, single element from a map mesh solid, and just see. With auto mesh, we have created 4 nodal tetrahedrons, and with map mesh, we have created 8 nodal hexahedrons. If we are going for low order meshing, we have just 8 nodes. If we go for high order meshing, it generates mid nodes, and so we have 20 nodal hexahedrons. So this is the difference that comes comes after we use auto mesh or the map mesher. Now with map mesher we have more structured meshing. So that was a very basic of what we have in auto mesher or the map mesher. So now what I will be doing, I will be using map meshing a face and auto meshing a face, and then using that 2D map meshed or auto meshed will be extruding those meshes to generate a 3D mesh solid. So in that case, having auto mesh and extrusion, we are going to create 6 nodal pentahedrals. Right now we have seen 8 nodal hexahedrons or 4 nodal tetrahedrons, but auto meshing a 2D and then extruding it to 3D, we are going to create 6 nodal pentahedrons. Let's see. So for this, let's create a rectangle. So I will be auto meshing and map meshing a surface which has a cavity in it, and then I will show how different map mesher features allows you to have control on your meshing, and at the same time having a structured mesh, having 8 nodal generating 8 nodal hexahedrons. So let's trim this solid along the curve, the surfaces along the curve. Select by. and same for this. So what we have created now, till now we have created two surfaces, and these are actually duplicate meshes. So we are going to auto mesh this face and map mesh this face, but you cannot. For auto mesh, let's auto mesh face and specify the element size, let's say 10. Specify the attribute, because it's a 2D meshing, we are going to specify a default attribute of 2, which we can change later, or we can say this is just a dummy attribute. We have actually created a structured quadrilateral mesh using auto mesh, and this is very much possible because all the dimensions are equal. You can end up creating a structured mesh, but now I actually want to create a unstructured mesh. So in advanced options, you specify just triangles, or you specify Delaunay, you specify any of the measure options, Delaunay measure, specify the triangles, play with the refinement factor if you want to, generate mid-side nodes for higher meshing, higher order meshing, and this is what you have created from your auto meshing a face. You have created 3 nodal triangles. From this, I will be extruding these 3 nodal triangles to generate 6 nodal pentahedrals. Next, we are going to map mesh this face, but you cannot use map mesh directly on a face which has holes in it. So it becomes a bit tricky, because in this case, we are going to create curves. And if I want to have only fine meshing near the cavity and coarse meshing outside, because it's just a wastage of time and money, I will say, to have equal meshing everywhere. So we'll take care of the size control along edge, specify the number of divisions which you want, let's say 4, and then you can linearly grade it. Specify the start length as 4 and end length as 10, and this is what you can do. Let's go more coarser. So now we are going to map mesh only this part of the surface using KH area. Select the edges of the area. Attribute, dummy attribute for 2D, again 2. In advanced options, you can go and generate mid-side nodes if you want to go for high order meshing, and you apply. Now we are going to mirror this mesh. Transform, mirror. We are going to select this mesh, the axis, so this way we have created a map mesh 2D. We have actually map mesh the whole surface. So let's hide all my geometry. This is what we have done till now. From these, we are going to extrude to 3D meshing. So mesh, protrude mesh, extrude. Select all the elements, the extrusion direction. Say the length is my 100 and number of divisions you want 10. Attribute for dummy 1, and you apply. Let's see the difference between a extrusion function that has been used on an auto mesh 2D face or a map mesh 2D face. So again we go to mesh, select a single solid from here, select a single solid from here and just show them. As expected, we have a 8 nodal hexahedron from a map meshing, but a 5 nodal pentahedral, 6 nodal pentahedral from extruding a auto meshed 2D mesh. So this is how you can have 8 nodal hexahedrons or 6 nodal pentahedrons or 4 nodal tetrahedrons using several options in GTS. So next what I'm going to do is going to use several protrusion features to generate a 3D meshing. So for this, let's translate this mesh in the desired direction. We are going to have, say, 3 copies more. And now we are going to use several protrusion features, accounting with the help of which we are going to create a 3D meshing from our 2D meshing. So mesh, protrusion mesh, extrude. We select the mesh, specify the direction, the length, okay, so we have one as for 2D, 3D. Next in the list is we have revolving. You can generate a 3D mesh by revolving a 2D mesh along an axis. Specify the angle, let it be 90. Here you have created it. Next, we are going to use the sweep feature. Again for sweep, or we are going to have a curve. So all we are going to do is we are going to first rotate this work plane, create a curve, and then we are going to sweep this generated 2D mesh to create a 3D mesh along that sweep curve. So again in this thing, my work plane is going to be XY, curve, create a spline curve. So after you have the spline curve, mesh, protrude mesh, and sweep. You specify the number of divisions as 10. Scale factor, you can also scale the mesh at the other end. So let's see, select the guide curve. This is what you have created. So next feature is we can also protrude a mesh using project, in which you can project the 2D mesh on some inclined surface or a vertical surface to generate the mesh shape of the required geometry. You can also use offset function, you can also use the fill function. So that's very simple and very common. So let's hide all and then use the most important thing now. We have to check the meshing, what's the quality of the mesh. So you can check the quality of the mesh, check mesh, how many free faces you have, and this is what you have created. Since they are intersecting, this mesh is going through this one, and this is very clear that you haven't taken care of the geometry. This meshing is passing through the other mesh, and these all are called the free faces. So removing these free faces becomes very important when you are working on a particular project. So that's all with meshing. Let's go back to the presentation. So different element types provided by GTS. GTS provide the line type, which are mainly the truss and the embedded trusses, the beams, tension only, compression only elements, and the plot only, which is a dummy for modeling, and also the geogrids. Apart from the line type, GTS also provides the plane type and the solid type, and covering others like point springs, the metric spring interface, elastic length, and the rigid lengths. But if I further bifurcate different line, plane, and solid types in accordance with which element I can use to model my soil element, or which element I can use to model my structure elements or various application elements. So for soil, we can use the solid element if you are working with a 3D model, or you can go for a plane strain element or axisymmetric element in case of 2Ds. And for structure element, you can create a structure element using truss element, embedded truss element, beam, plate, or plane stress element, where very importantly in GTS you can specify the sectional properties. Like for a truss element, you can specify the radii of the truss you are using. And further application elements, you can use the various interface elements, pile tip bearing elements, various rigid length, elastic lengths. So as I explained, for every mesh solid, mesh solid which you have created is going to have an attribute. So an attribute is just a reference to which its property, its material, and the element type is going to be referenced. So you can create a new attribute by several types provided by GTS, either of the line type, where you need to take care of the property. You can also define an attribute using plane type, where you need to take care of its, again, material and just the property. For solid type, just taking care of its material, spring, or the length types. So this way you define the attribute of the element you are working with, whether it be 2D element, 3D element, line element, plane element, or any structure element, or any other application type. And these are the several ways with which you should define the attribute of that element. Various material models provided by GTS. GTS provides several structural constitutive models, geotechnical constitutive models, and CPRES constitutive models. So, but if I bifurcate these constitutive models in as linear elastic constitutive model, as elastic or elastoplastic. So first in the list is we have linear elastic constitutive models. The linear GTS, actually the motive of why we have several constitutive models is we want to simulate as closely as possible the real scenario which is present in the outside world. You can specify the ductile brittle rocks, you can specify the clay, you can model soils, you can take into account the granular nature of the cement also. So these are different constitutive models with the help of which you can actually simulate the real behavior of the ground. So in linear elastic constitutive model, we have linear elastic models, which is based on a linear stress-strain relationship. We have transversely isotopic models, with which you can account for multiple incline layers, and in this the input parameters correspond to normal and tangential direction of the stratification. You have D-min model. It is a linear elastic model which is usually used to simulate rock materials, both soft and hard. Next in the list is we have non-linear elastic constitutive models. So starting with non-linear elastic models for truss and embedded type, with which you can define a compression only behavior, gap behavior, tension only, and hook, and as well as user defined multilinear behavior, each having its own stress strain relationship. Non-linear elastic model for elastic links, with which you can account for the general rigid, tension only, and compression only behavior of the elastic link. The geomembranes, these are reinforcing structural material to improve the strength of the soil by providing additional tension. The plate interface model, these are used to account for large shear forces, and this becomes this is highly used when it comes to actually simulate a TBM, tunnel blasting method, in GTS. So for lining and the interface elements, we use plate interface model. We have nonlinear pile model, with the help of which you can account for the force transfer that is taking place between the soil and the pile elements, and as well as you can account for the relative displacement that is taking place between the soil and the pile elements. We have Jardine model. This is a nonlinear elastic constitutive model, which is also called the London clay model, and this is mainly used to simulate clays. The basis behind this is it combines nonlinear elastic behavior with ideal Tresca plastic behavior. Next on the list is the various elastoplastic constitutive models. Beginning with various interface models, these are based on the Coulomb's law, and these are used to simulate the interface behavior of the pile and the surrounding soil, retaining wall and the surrounding soil, lining and landfills, jointed rocks, and fault zones. We have Tresca model, which is used to model cohesionless soil as well as undrained behavior of the ground soil. We have von Mises model, which is used to simulate the analysis of ductile materials. This is mainly used for simulating anchors, nails, or steel-made pile pipe. We have Mohr-Coulomb or the Decker-Prager models, which are used to model granular materials like soil and concrete. The Duncan-Chang model, also called the hyperbolic model, this is mainly used to simulate the gravel behavior, and this has a hyperbolic stress-strain relationship. That means as we increase on higher strain, this approaches non-linearity. The strain softening model, this controls the softening of the soil. The modified CAM clay model, this is used to simulate clay, and this finds its high application in consolidation analysis. We have jointed rock model. This is used to simulate the behavior of stratified and jointed rock masses. In this, you can also account for the elastic and plastic anisotropic behaviors. The Hook-Brown model, to account for the brittle failure of the rocks, we model using Hook-Brown model. In this, we can account for the failure of a jointed rock mass in response to induced stresses. We have modified Mohr-Coulomb, which is with the help of which we can account the hardening behavior of soils. And lastly, we have seepage constitutive models, mainly called permeability function and the volumetric water content function. With permeability function, we can account for the seepage flow using the permeability coefficient, as we know, which is obtained from the Darcy's law. And using volumetric water content function, we can account for that water which is retained in the soil. That is, we can account for the unsaturated soils using volumetric water content functions. Coming over to the various analysis capabilities which MIDAS GTS provides. In MIDAS GTS, we can do static analysis both of linear and non-linear type. Construction stage analysis of drained and undrained type can also be performed in GTS. We can also perform seepage analysis of steady state, or we can also have transient seepage state analysis in GTS. In this, we can also account for the saturated and unsaturated nature of the ground. We can also have a semi-coupled analysis, with which we can see the effect on construction stage. We can see the effect of changes and stresses that is caused due to the poor pressure of water that is present. So this is a semi-coupled analysis. But if we want to go for a fully coupled analysis, GTS also provides consolidation analysis. In GTS, we can also do the slope stability analysis, mainly strength reduction method or stress analysis method, which is a hybrid of our limit equilibrium method as well as our strength reduction method. Apart from this, we can also go for the dynamic analysis, mainly eigenvalue analysis, the equivalent linear analysis for 1D. For 2D, it's in development and it will be released very soon. We can also go for response spectrum analysis, the time history analysis, again for linear. The non-linear is again in development and will be released very soon. So depending on various application capabilities of GTS finds its application in deep foundations and soil structure interaction, where you can account for the you can use 3D modeling to account for the pile-wrapped foundation for very high-rise buildings. GTS finds its application deep excavation, temporary structures. We can also model unconventional tunnel intersections, which we will be demonstrating in our coming educational webinars. We can also account for tunnel blasting method analysis, considering various excavation sequences in GTS. Vibration analysis for earthquake and blasting can also be done in GTS. We can also account for the dynamic effects of high-speed train. The underground structures, the subway, disposal facilities, etc. can also be modeled and analyzed in GTS. The groundwater flow, taking care of seepage phases, and the coupled analysis can also be done in GTS. GTS finds its high application in the slope stability and slope stability of dams and embankments. So lastly, in the list we are left with the tunnel modeling wizard. You can model the whole tunnel using just defining the basic tunnel configuration, then defining the shotcretes and the rock bowls, defining the excavation stages, defining the mesh, and taking care of the post data. So with very small input of data, you can actually model the whole 3D tunnel, and also taking care of several construction stages. Next, modeling wizard, GTS provides anchor modeling wizard, with the help of which we can model the anchor, taking care of its material as well as property. So I would like to conclude here with my presentation. So you may proceed on with your questions. So now I will be entertaining some of the questions. I would like to emphasize here today, actually we got a query that some user wanted video, but I am sorry to say that this time we are not providing the video for this first education webinar, but for next education webinar we might consider. So let's see the questions we have. You may ask your questions. We have a question from Aslan Gahmani. Does GTS do seismic analysis from initial stresses? I repeat, we have a question. Does GTS can do seismic analysis from initial stresses? Yes, GTS performs seismic analysis on the basis of initial stresses. Can I see next question we have from Mr. Stanley W.K. Shum. Can I see the soil movement in animation using GTS under earthquake? Yes, you can see GTS provides you with various post-processing features, with the help of which you can also create the animation. You can also take into account the soil movement in earthquakes. Next question we have is, can GTS handle tension cracks in soil? Yes, I would like to inform that on the basis of several constitutive models we can take into account the tension cracks which is available in soil. We have several constitutive models which can be used to even account for the fault zones and the jointed rock masses. Next question from Mr. Ala Korde. Can GTS study the effect of interaction soil structure frame? Yes, with the help of various interface elements we can account the effect of interaction between the soil and the structure. The next question we had from Mr. Hamid. Do this software give us the interaction between the soil and the structure? I would like to repeat again, on the basis of several interaction elements we have in GTS, we can account for the traction forces that is going to take place between the structure as well as the soil, as well as we can account for the relative displacements that are going to take place. Next question we have from Mr. Alex. Can GTS solve sheet pile walls and seaports? Yes, and I would like to inform that GTS has found its application in this regard. GTS can solve sheet pile walls, solve and analyze sheet pile walls and seaports. Next question we have from Mr. Nyolata. Does GTS identify the characteristics of soil? As I explained, we have several constitutive models, 19 in number, with the help of which we can very accurately simulate the required characteristic of soil, whether it is clay, whether it is granular soil, whether it is rock, or even defining the brittle nature or the soft or hard rock. So GTS differentiates between various characteristics of soil. We have another question. How can we use geometric or large displacement option in time history analysis? Actually, we don't have this geometric or the large displacement option time history analysis now in our program, but this in a coming release in June we will be adding this feature in GTS. So the latest version market is 2010 version 1.2. So this is available at our midasuser.com or the so-called Moose, from which you can download it and enjoy the evaluation version. Another question we have is, I wonder if you have planned to include unsaturated shear strength model in GTS. We have a question. Mr. Sunki Nam is asking about the plan to include unsaturated shear strength model. Sir, we have several constitutive models, and I would like to have some more information about the question you are asking. So for that, you can email your query on esupport@midasit.com, with which we can let you know that which constitutive model can help you in this regard. So next question we have from Mr. Bridget Mulani. Can we assign water table? Yes, we can assign water table. We can assign several nodal faces, as well as we can also assign a global waterhead in our construction stages or in our model. We have a question asking for the PowerPoint presentation. For this, I need to discuss with my company, and then after discussing that, we will send you the PowerPoint presentation, if possible, to your email ID. We have a further question from Mr. Stanley. How can GTS tell us whether the soil is liquefied under an earthquake? Mr. Stanley, we are going to include liquefaction analysis within 1 month release. So after that, performing liquefaction analysis, we can account for the liquefied soil. Mr. Alex, we have tutorial for the demonstration of sheet pile walls, but for that you need to contact us on our esupport@midasit.com so that we can help you with our support. We have a question from Mr. Hamid. Is this contain the time interval between construction stages? Since we don't have any in consolidation analysis, we can control the time interval between construction stages. We have a question from Mr. Asalan. If I do static analysis for earth dam, can I do seismic analysis that includes static stresses? Yes, Mr. Aslan, you can do seismic analysis, first performing an eigenvalue analysis and then time history analysis that will include static stresses. We have a further question from Mr. Alex. In sheet pile walls and retaining walls with anchors, does GTS consider the anchor movement due to material elongation? Yes, Mr. Alex, we can account for the relative displacement that is taking place between the anchor as well as the sheet pile or the retaining walls, and because of this, the traction forces that are developed, we can account using various interface constitutive models we have in GTS. We have a further question from Mr. Ali. How to input damping factor of soil in MIDAS GTS? You can input the damping factor of soil in MIDAS GTS and time history analysis, where either you can go for stiffness calculation either on the basis of most nodal mass participation that you have obtained from your eigenvalue analysis. So going okay, I would like to demonstrate this factor, how to input damping factor of soil in MIDAS GTS. So in model, I think this, in model load so in model load, and then we have time history data, ground acceleration. You can specify the time history load set. And here you specify the whole ground acceleration. So for that we need the creating surface plane. So element, and we create a surface spring, and this surface spring we include the damping constant per unit area. So this way we can account for the damping constant and MIDAS GTS. So next question we have, concerning the slopes. We have a question from Mr. Ala Korde. Concerning the slope stability, could we use a model other than Mohr-Coulomb using SSR? So we in MIDAS GTS we can perform slope stability using SRM, which is strength reduction method, or stress analysis method, which is a hybrid of limit equilibrium method or strength reduction method. So please let us know with your email on esupport@midasit.com concerning more detail about SSR. We have a question from Mr. Hamid. Do this software gives us the factor of safety for excavations? With after going for slope stability analysis, either by using strength reduction method or stress analysis method, which is again a hybrid, we can account for the factor of safety for excavations. We have a further question. Can MIDAS GTS can perform geogrid analysis? Yes, on the basis of geogrid elements, we can perform geogrid analysis. We have further question from Mr. Ning. What is the next webinar for advanced Gen GTS, such as applying data for soil seismic load analysis? Mr. Min, this will be informed to you by our company. We will be, I would like to inform that we will be sending an email by tomorrow with the help of which you can specify whether you need a certificate for attending this webinar, and after this follow back, we will let you know about the further information about the upholding webinars we have in near future. So I would like to conclude today. I would like to thank everyone for your precious time. It was really a nice time having a educational webinar which is first of its kind in the series. Now we will have the next educational webinar in the next month, which will be more advanced than this basic webinar. So hope to see you the next time. Thanks a lot. For more questions, mail us to esupport@midasit.com.